Alright, algebra students, hopefully these videos will allow you to still get the same content as if I were there. Obviously, I'm not there to answer your questions, but I feel confident that you've heard what I want you to hear, and I can always get your questions answered when I return. Okay, I do ask that you take notes from these videos, just like you would if you were in class. If it's an assigned video as part of an assignment, I will start giving you credit for those. So let's just practice today on taking notes. You're always welcome to pause the video, obviously. There will be times that maybe I will ask you to solve a problem, and I'll tell you to pause the video. But just like if we were in class, take notes, and hopefully this will allow you to pause and rewind or review if you didn't catch something I said. Whereas sometimes in class, if I keep going and you didn't get a chance to ask a question or hear it a second time, this might be better for you, okay? So we're going to start chapter 5, and just like chapter 4, a lot of the stuff at the beginning is review. So that's why we're actually looking at 3 sections today, because they're all very basic review. I don't think you'll have any issues, but we will do some examples just to refresh your memory, okay? So chapter 5 is all about linear sentences. Linear being line, sentences being we have a verb. Those two things we've talked about a lot this year, so I don't foresee this being a huge issue for us. Alright, so the first section we're going to look at today is section 5.1, which is horizontal and vertical lines. Alright, so what I'm going to do is just draw a quick little set of axes. They don't have to be perfect, but this will just help us look at some things. I think most of you know what a horizontal line looks like and what a vertical line looks like. Horizontal looks like the horizon. Vertical, I just always look at the direction of when you make a V. It's mostly up and down. Okay, so that would be vertical. So I'm going to go ahead and draw one of each of these. So let's see. Okay, I just put some tick marks on for our scales. So here's a vertical line. Okay, I want you to go ahead and draw 3 points on this vertical line and label their coordinates. Okay, draw 3 points on this vertical line, label their coordinates. Alright, so I'm just going to pick 3 points. I'll pick this one, here, and here. Okay, label their coordinates, so 5, 3, 5, 0, and 5, -1. Okay, you didn't have to pick the same 3 points. We know there are infinite number of points on this line, so we could have all had different answers. But what will be the same on all of our answers, regardless of who did this, if you did it correctly, notice that my x values were all 5. Okay? That is how we figure out the equation for a horizontal line, or vertical line in this case. Same thing goes, though, for a horizontal line, as we'll see in a second. Okay? So the equation for this vertical line is x equals 5. Okay? A lot of students always get this mixed up because they think, well, this is the y-axis, kind of, so it should be y equals. But go back to what are the points on there, and everything was at x equals 5. We went 5 in the x direction. Okay? So we're going to do the same thing with a horizontal line. Okay? So go ahead again and pick 3 points on there, label their coordinates. look at your points, look at my points. Again, you can have totally different points, but there should be something consistent about your 3 points. That consistency is the same with my 3 points. Notice they all have a y value of -1, because what we did was we took the whole line and shifted it down 1 in the negative, down 1 in the y direction, so a -1. Okay, again, that will give us the equation for a horizontal line. Okay, so vertical lines will always be x equals. Horizontal lines will always be y equals. However you need to remember that, please do, because there will be easy questions on homework and quizzes like, what is the equation of this line? So you just figure out, oh, I went over 5 in the x direction, or I went down 1 in the y direction. Okay, so that's really all we need to talk about for horizontal and vertical lines. If you know that much, I think it'll be just fine for you. All right. The next section, 5.3, is solving some equations, which a lot of you are probably extremely excited for because you like doing this. Okay, and maybe this looks like we've done this before, but this is the first time that we in this class have looked at any equations with variables on both sides. I know you've done it in Mrs. Lee's class, that's why I'm not concerned with us having any issues with it. Okay, so this would look like something like this. Could you go ahead and solve this? I have no doubt you can. Just some suggestions. Our whole goal is to get all of the variables to one side, either left or right, it doesn't matter, and all of the numbers to the opposite side of that. Personally, I always just evaluate my variables first and decide, should I subtract 2w from both sides, or should I subtract 5w from both sides? And I like to keep my variables positive, just makes it easier when we get to equation or inequalities. So if this was me, I would subtract 2w, get 3w plus 1 equals 13. Since all of my w's ended up on the left, I then need to take my numbers to the right. And then this looks, really, after that first step, this looks like any other equation that we've done so far this year. And then you can just go ahead and finish that, like so. Okay? And that's all there is to it. Another example is actually easier than the first one we did, but sometimes trips up students because there's variables on both sides but not numbers on both sides, so they don't know what to do. Personally, I just want to do fewer steps. So if there's only a number here, I'm just going to make this my number side, meaning I'm going to add 7y. Don't forget that negative on your 55. Okay, so that's what equations look like with variables on both sides. I'm actually going to look at an example from your book that is on page 300. So this example 4 here, again, I always talk about how we're unfortunately not going to just have to solve random equations, or probably going to have to write the equations before we get to solve them, so I think this is a good problem to practice that. In 1990, the population of El Paso, Texas was 515,000. In the 1980s, its population increased at an average rate of 9,000 people per year. In 1990, the population of Milwaukee, Wisconsin was 628,000. And in the 1980s, its population decreased at a rate of 800 people a year. If these rates continue, in what year will the populations of the cities be the same? Okay? The big idea here is the fact that these two situations, we want to make them equal. Okay? So that's what you want to keep in mind when you're writing these longer equations is what am I going to set equal to each other? Well, since I want these populations to be equal, I'm going to put my expression for Milwaukee on one side and my expression for El Paso on the other side, and I can solve them for the variable, and that will tell me how many years it's going to be until they are the same. Okay? So let's go ahead and find the information on El Paso. Was 515,000 increasing at 9,000 people per year? So I have 515,000. I'm going to add 9,000 people per year. Okay, and I want to know when that population is going to be the same as 628,000 decreasing at 800 people per year. Okay, so El Paso, Milwaukee, and I want to figure out what y is because that'll tell me in how many years they will be equal. Okay, so again, I'm going to look at my variables and I'm going to add the 800 y. So then I'm left with 9,800 y, and then I'm going to subtract the 515,000, sorry. Okay, and then divide by 9,800. So I have 1,130 divided by 98. Let's make sure we have that right so far. Looks like 11.53. But what does that 11.53 mean? Okay, the question says, in what year will the populations in the cities be the same? Okay, so if we look at the explanation the book has, it's written very well. 11.53 years after 1990. So 2001 or 2002, depending on when in 1990 they were taking this data. Okay, so either 2001 or 2002. Okay? All right, so then the last section is very, very similar to this. 5-6, which is solving inequalities with variables on both sides. And again, this is the third time we visited some sort of inequality. So let's remember what is the one thing that is different about inequalities than equations. That one big thing. Hopefully you all remember that if we multiply or divide by a negative, we must flip the symbol. Okay, so multiply or divide by a negative, we have to flip the inequality symbol. Alright, so let's just do a couple of examples to refresh our memory on this. I'm looking in your book, actually. Okay, this is page 317. This has a little bit of information about some tree growth. Okay, many species of trees grow at rates that are nearly constant. Some years ago, the Lee family planted 2 trees, a beech tree that was 8 feet tall and a maple tree that was only 3 feet tall. Maple trees grow at about a rate of 1 foot a year, and beech trees grow more slowly at about a half a foot a year. So t years after planting the height of the beech tree is the original 8 plus half a feet per year, and the height of the maple tree would be the original 3 feet plus 1 t feet per year. Okay? So this example says, Mr. Lee looked at an old photograph of the two trees. In it, the beech tree was taller than the maple tree. He wondered when the photo was taken. Well, we can use these two expressions, okay? We want to know the beech tree is taller, so greater than the maple tree. So the beech tree, which we said was 8 plus half t, and the maple tree 3 plus t, okay? Again, I use the same idea of keeping my variable positive if I can. It doesn't matter, you'll get the right answer, but I just like to keep my variables positive if at all possible. So I would subtract half t. Okay, so I have 1 minus a half, so I end up with half t. And then I would go ahead and subtract my 3, so I end up with 5. Okay, right now I have 5 is greater than half t, so divided by 0.5, divided by 0.5, 5 divided by half is going to be 10. Okay, so again, what does this answer mean? Okay, a question was asking us about when the picture was taken. He wondered when the photo was taken. Remember, t referred to how many years it was growing. So let's look at how the book words this. The photo was taken less than 10 years after the trees were planted. Okay, because this is saying that the amount of time the trees were growing was less than 10 years, so anywhere before 10 years after they've been planted. Okay? Let's look at another example from your book. Example 3. Okay? Again, this is just practicing writing them. I think you're okay with solving them, but sometimes writing them is the hard part. Alright, so this says 3 times a number is less than 2 times the same number. Okay, I don't know what that number is, so I'm going to call it x. Okay, so 3 times a number is less than 2 times that same number. Find the number. Easy enough. Go ahead and we will solve this. So I could subtract 2x, get 0. 3x minus 2x is x. So this is saying that x has to be less than 0. So what could x be? -1, -2, anything, but if you think about it, 3 times any negative number will always be smaller than 2 times that number. Okay? So that's it. Horizontal, vertical lines. Solving with two equations, or solving with two variables with equations, and solving with two variables and inequalities. Alright. Thank you. I will see you soon.